about 23.5 degrees, and because of this axial tilt, our planet has seasons. Basically, the winters in the north hemisphere are colder, while the summers are warmer, and the opposite happens on the other side of the planet. But every 41,000 years, the planet starts tilting a little bit. Basically, it goes between about 21 degrees and about 24.5 degrees. So this happens every 41,000 years. And to try to understand why this happens, you just have to look around our solar system. Giant, massive planets like Jupiter can easily influence the orbit of pretty much any planet in the solar system, including, of course, Earth, and even change their axial tilts and influence them in many other ways. So the axial tilt changes because of the planetary interactions. But here's the thing though, if you look at Mars, the axial tilt here is actually higher, and we think that it changes even more according to our simulations. It goes from between about 10 degrees to about 60 degrees. So there's actually a 50-degree difference compared to only like a few degree difference that Earth has. Why is that? And by the way, this is also one of the major reasons why Mars couldn't really maintain liquid water or atmosphere. Obviously, the loss of magnetosphere was one thing, but because it also wobbled so much, and it does so every 2 million years or so, once in a while, especially like when it's this way, a lot of the atmosphere will get condensed and form ice on the poles. But when it's this way, same happens along the equator belt. And eventually all of the atmosphere kind of disappears and becomes ice. So we think that this actually influenced the formation of ice on Mars, and also would prevent really complex life from evolving on Mars because it just doesn't have stable conditions like our own planet. But what's the difference? Why does Mars wobble and Earth doesn't? Can you take a guess? You probably already know the answer. Except for size and mass, what other major difference there is between these two planets? Well, the answer is that our planet has a really, really large, really massive moon, whereas the moons of Mars are ridiculously tiny. Now, in case of our planet, technically this is actually an anomaly. Our moon is way, way larger and way more massive than moons of any other planets in comparison to the planetary size. As a matter of fact, certain scientists kind of refer to our moon-Earth system as a binary planetary system. Some people don't even think that this qualifies as a moon. But what this object does to our planet is remarkable. Our beautiful moon actually stabilizes the axial tilt of our planet by orbiting around it. It sort of acts in the same way that the disk of a typical spinning top stabilizes it as well. So the orbit of our moon around our planet prevents the planet from tilting too much. And this, in a sense, presented our planet with a chance to have really, really stable climatic conditions for a very long time, and most importantly, allowed for complex life to evolve here over billions of years. But remember, our moon was a bit of a fluke in the way that it was created. Today we believe that our moon was created as a result of a collision with a Mars-like planet approximately 4.5 billion years ago, and its creation is not guaranteed. A collision with a planet would not necessarily create a moon-like object. This was, in a sense, a very lucky formation. And since not all planets out there are able to have moons to stabilize their axial tilt, it's very likely that not all terrestrial planets are going to be able to maintain stable climatic conditions. So now going back to the binary systems, can a binary system stabilize a terrestrial planet in the same way that the moon does? In other words, these scientists behind this paper wanted to investigate if by being in a binary system, a typical terrestrial planet in the orbit around one of the stars would actually receive the same effects in stabilization of its axial tilt as Earth does when the moon orbits around it. And as you can probably guess, what they discovered is that there are certain situations, actually many situations, where binary systems are perfect for stabilizing axial tilts of planets. And by using our nearest neighbor as a kind of a foundation for the simulation, they were able to create a model that investigated the effects that binary systems would create and discovered the necessary conditions for the most stable binary system where a typical terrestrial planet can exist. Well, first of all, the bad news is that it seems that our neighbor, Alpha Centauri, might not actually be the best place to discover such terrestrial planets that would be stable and would have the necessary climatic conditions. mostly because these two stars are just a little bit too close to each other at a distance of about 35 astronomical units. And the scientists behind this paper discovered that to have the most likely chance for a stable terrestrial planet with Earth-like conditions, either the primary star would have to be small, so about 80% the mass of our Sun, or the distance between stars would have to be much larger. So, for example, since Alpha Centauri is about 10% more massive than our Sun, it sort of falls under this area here in the middle, and for it to have about 90% chance for a terrestrial planet to have